Okay, so this is probably large enough that you can actually see what's on my screen now.
Yes.
Okay. All right, so when we are gonna do graphing and stuff, in this case, it doesn't matter too much whether or not I select the data in the right order, because I'm gonna check in a second. So I'm gonna insert up here at the top, and I'm gonna graph it. And that part's okay, right?
I can do that part, yes.
Okay, so I can see this graph has a decreasing exponential curve, which is what I want. It didn't get my stuff on the correct axes, but I don't really care because I'm not going to keep this graph anyway. So I'm just going to delete it again. And now I want to do the analysis. So the analysis that I'm going to do, if I want to check for first order, then I'm going to need natural log of my concentration to F4 versus the time. If it's second order, it's going to be 1 over the concentration, C2 F4. So I'm just going to go ahead and line up my columns and get them ready. So can you do the calculations okay, where we say equals natural log?
Yes,
Okay.
I did that, and I did the 1 over.
Cool.
306, got that. 26. Okay, I did something wrong on that one because I got a. Where you have a 10, I have a like hashtag divide. I think it's because I'm dividing by 0.
You might be dividing the time instead of the C2F4.
Oh, so you're doing both columns by the C2F4?
Yeah, because it's both of them are based on the C2F4. We're not doing anything to the time.
Oh, okay.
Yeah, time we just leave alone.
Okay, that's my mistake.
Yep, so that's an easy fix. So then when I graph these guys, I'm gonna pick them one at a time. So I'm just gonna take my natural log of the concentration and I'm gonna insert another chart. And it's already looking pretty linear, but I'm gonna make sure. So I'm gonna go up here to select data so I can put in my X values, and those are the time. Okay, and then I'm gonna change this chart title so I don't lose track of what it is. So this is possible first order kinetics or some other title. And I'm gonna put in my axes labels. Natural log. Delete the rest. And then okay. Now this is a irritating graph because they give me so much space over here on the y-axis. I'm gonna fix that because I want to be able to zoom in more on my curves. So I don't need it to go all the way to 0. I'm going to come over here. I just double clicked on that axis. And I'm going to come over here to those columns and go to axis options. And I'm going to make my maximum like -2 and see how that looks. Alrighty, it's looking a little bit less linear here. And so I'm going to add in a trend line, more trend line options, and we'll see what that equation in R squared looks like. So far, so good?
Yes.
Okay, now we're gonna do it again.
What's the R squared telling you?
It's telling us how good the fit is.
Okay.
So like how far we are from an exact match.
Okay, pretty close.
And so it's not a bad match, but we also only have 5 data points. And so So it's a little bit ambiguous still. So we're going to plot this 1 over and see what happens with it. See if we can tell the difference between our two graphs. So this one needs to be graphed against time also. So let's put the time values in.
And how do you know it's a possible second and not a possible first on that one?
Because that's the graph that I'm making. The graph that I did just now is the 1 over, and if that one has a linear relationship, it's a 1 over the concentration with time. And if it has a straight line relationship, then it means that I have second order kinetics. That's the purpose of graphing it.
Okay, and this might sound stupid, but by saying possible, does that mean it could possibly be our first order as well?
No, it's going to be one or the other. So the reason why I titled it possible is just because we haven't committed yet. We're still looking at our data to find out which of our fits they are.
Okay.
So I'm only leaving them as possible first order and possible second order until I look at what the R-squared values are like.
And see, the natural log ones could only possibly be a first order.
Yeah, so this is always our test for first order kinetics, is taking natural log of the concentration versus time.
Okay.
And if we have a straight line relationship for the natural log of the concentration versus the time, then that's showing us that yes, we do have first order kinetics. If when we do this graph over here, which we just did, we do 1 over the concentration versus the time, and we get a straight line, and this is a better straight line. Notice that the R-squared is 1. And so this one indicates that we do have second order kinetics.
It's a better fit. Okay.
So then I'll probably say, nope, not first order kinetics.
Okay. I think that makes sense, especially if I go back and watch this again.
Yeah.
So that would which rate law it is.
Yeah, so that tells us what our rate law is with the C2F4. So we would write that rate. I don't know if I have a draw option. I do have a draw option. So this would imply that our rate would be the rate constant times C2F4 squared. And that would be our rate law.
Okay. That makes sense.
And let me label the chart. It's not very good at going back and forth between the pen tablet and the not the pen tablet. All right, let's add those labels, so then we'll know what we graphed. Yep, no, we're still doing titles. And in case it was not totally clear yet, when I use these square brackets for the chemical formula, the square brackets is shorthand for concentration of. And so that's what's implied anytime we have those square brackets around some chemical name, that means concentration of. So
yeah, and it took me a while, but I started suspecting that was the case.
Yeah, I tried, because I know, I've got a group of people from a wide range of different science paths here. And so I tried to make that clear, or, to kind of like emphasize it a few times, just to make sure that everybody was catching it, because it's something that, you get used to just doing, but you have to have been introduced to it at a certain point.
No, you probably said it. I have 36 pages front and back of notes, and so it's probably in there somewhere.
as I said, it probably was not something that I specifically defined at any point, but I just tried to make sure I said it, you know, a few times. So, but yeah. Well, 36 pages of notes, that's not too bad. You should see my stack.
I'm sure you've been doing all the videos. You probably got a ton of stuff.
Yeah. Yeah, I have quite a stack of notes. I mean, I'm wordy and I'm old fashioned because I like to write things out by hand first. But whatever works, right?
Exactly. I'm trying to use too much of your time here. So, assignment 9, question 1.
Yeah.
Particular reaction has the following rate constants at a range of temperatures. Determine the activation energy and the collision factor.
Yeah.
Is that something we can graph? We graph that one too, correct?
Let's see. Equation 1, yeah. Or problem 1. Yes, we can.
That's just the same thing, like y equals natural log of k.
Yeah, so let me share that assignment. Where are we? Right there. Okay, so if we just kind of look ahead really quick here to the next one, to problem 2, this is sort of the version that we are referencing here, that we've said the Arrhenius equation is not A, E. A happens on the other side. Okay, so we have K equals A, e to the minus E sub A over RT. So if we take the natural log of both sides and move the A part over, then this is the equation that we would get. And so, except I wrote a K. Let me get that right. Here we go. It's the K. So if we rewrite this, then we can use this as our y-axis, and this is our b, and this is our m and x. So y is equal to natural log of k, and so that's what we're going to do with these k values. We're just going to, in Excel, calculate natural log of k, and then x is equal to 1 over t, and so we're going to do that over here to this column, take the 1 over t for those guys, and then we're just going to plot them, natural log of k versus 1 over t, and we should get some kind of a straight line. And the intercept will be the natural log of a, so we can calculate a from wherever we hit that, and that'll be the equation of our line, right? Because Excel will give us one, so we can just use that. And then the slope will be minus E sub A over R. So we can just take that number, multiply by R, and get minus E sub A. So we'd have to, I guess we'd multiply it by minus R.
Okay, and that was it was like 6 or 8 something. I wrote that down.
Yeah.
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 Okay. So let's see. So the activation energy would be EA, and the collision factor is. That's good for me. Which one's collision factor?
Just this A.
A. Okay. Okay. You even put it in here. Yep. Collision factor A.
Yeah, you know, it is well known in educational theory that you have to repeat something at least 6 times before you learn it. So.
Yeah, repetition.
No problem.
Yeah.
So I just consider it's all part. If somebody asks me the same question like 3 minutes apart, I just answer it again. So.
Yeah, I appreciate you. Very patient. I've seen your videos. You answer the same question sometimes every other night. So.
Yeah, you know, I mean, as I said, people are at different places, and so I don't say we did this 2 days ago. Plus, that would be rude. So.
Yeah.
So I just answer it again.
Yeah. Let's see. I forgot that this was one of my questions I was going to ask you. So the one right underneath the number 2, I don't have a really prepared question to say because I forgot about that one, but another form of the equation allows us to eliminate the collision factor A.
Mm-hmm.
Calculate the activation energy. So this is just doing the same thing, but by hand?
This one is really just algebra. So when I was teaching the Arrhenius equation, it's pretty common to follow the description of this part of the equation and the graph with this additional one. And I thought, I don't know if I want to, confuse people with another equation in the lecture part. But if we take this equation at one temperature, right? Because this is for one temperature. The K value for each K, or for each T, we have a K value. And so this graph represents it at multiple different temperatures, and in fact, any temperature. But if we have just 2 temperatures, then we can subtract one version of this equation from another version of this equation and get rid of the 2 natural log A parts. And then you just get this equation right down here that I've put in problem 2. So it's a lot of, there's a lot of symbols here, but the information in the equation, we have 2 temperatures, right?
Mm-hmm.
And we have 2 K values, this guy and this guy. And so those are these dudes and those dudes. R is the gas constant. So it really is just solve for the one unknown. So it's just an algebra problem at that point.
Okay. And then the order. So you don't want us to graph to find the order on this one?
No, you don't need to. So you may or may not have clued into it yet, but if you have not, then I'm happy to share it.
Assume I haven't.
Well, it's subtle. And even when I mention it, it's subtle.
Mm-hmm.
So when we look at rate laws, so let's think about a first order rate law. And we think about the units. I'm a big believer in looking at units. Mm-hmm. So rate is always going to be something like molar per time, right? And then the concentration is in molar units. So what's the rate constant?
What's it in?
Yeah, what's its units?
Oh, is that seconds?
It's 1/seconds, right? Because these have to be equal.
Yeah.
So now let's look at a second order. So rate still has the same unit. This is now molar squared. So what do the units have to be on the rate constant?
Molar over seconds.
Is it molar over?
Oh, no, you gotta have molar to cancel out the other molar.
Yep. So you're gonna have 1/seconds and molar.
Okay.
Cancel out that dude. So what about a third order?
The 1/seconds time. Yeah, 2 molars then, right?
Yep. So you can always tell what order the overall reaction is if you can see what the units are on the rate constant, because they always have to cancel. Oops, I just put a K instead of an S. They always have to cancel out everything else on that right-hand side to get us molar per second or molar per minute or whatever. So if you can see those units on the K, then you know what the order is automatically.
Okay, so this is definitely a first order.
Yep.
Okay. What could you have them if they were like a first order for the first one, second order for the second one? Or would that just be a third order?
This one, This guy right here?
Say that, like, for instance, the 7.56 times 10 to the 6, if that was a second order one, would
Then
that,
what would be the units on it?
you'd be 1 over meter or molar times, or seconds times molar?
Yeah, you can write it either order. Yeah, if it were a second order, that's what its units would be.
Okay.
Typically, and this doesn't 100% have to be the case, but typically, if you have a reaction that is first order at one temperature, it's probably going to be first order at another temperature. Occasionally, if you have really big temperature differences, you might get into some different kinetics for the reaction, but we aren't going to worry about that. So
Okay.
we're going to keep things simpler than that.
If you did have that big temperature split though, and you had a second order with a first order, you just add those for like question B, where it says which order is it? Would you say third order?
So no, you would, so if I had at, 100 Kelvin, the rate constant is something or other 1 over seconds. And at 1000 Kelvin, then the rate constant has units 1 over molar seconds. Then I would have to ask, what is the order at each temperature? And then you would say, at 100 degrees, it's first order. At 1000 degrees, it's second order. Because they would have two separate, probably separate rate laws and separate rate constants.
Okay. Okay. I think I can find that.
Yeah.
Then I'm not sure if I have any problems with. I think it was like a 2-minute block on Half-Life.
Yeah. But I can talk about Half-Life if you have questions.
Yeah, that'd be my last question. So.
Okay. Yeah, no problem.
Tabbed it out.
Come on.
Then negative KT natural log.
Yeah, but I actually want to talk about, if we're going to talk about Half-Life, I want to talk about Half-Life from a sort of a deeper understanding position, because if we just say, T1/2 is equal to natural log of 2 over K, which it is for first order reactions, then that's okay, except that it leaves you with no place to go for anything other than half-life and for any other order. So if we think about what a half-life is instead, the half-life is the time it takes for half of our stuff to go away. Mm-hmm. So that means that at time 0, we have, we'll say x sub 0, right? And at T1/2, we have some concentration that is equal to half of that initial concentration, right?
Yep.
So if we have a first order rate law, then that rate law K over, or K times X, right? What do I want to do with that one? Hold on. Why do you keep doing that? I just want the color. Okay, anyway, so let's say that instead of a half-life, I want to do like the time it takes for 90% of my stuff to go away, just as another time point. Then my X for this particular point, how much would be left? How much of the original amount would be left if we had used up 90%?
10%?
Yeah, we just have 10%. So instead we can just multiply that initial amount by X, by 0.1, right?
Yeah.
To get us to the amount of the concentration. So now if we think about those half-lives, let's see. Which one is that even in?
The video?
There we go.
No. Chemical kinetics.
So when we look at our half-lives, Then we want to think about those integrated rate law relationships. So for our first order integrated rate law, first, I'm going to need more space. I don't need all those numbers. Okay. So our first order integrated rate law we are looking at those concentrations from a natural log standpoint, right? And that's the whole point of us graphing the natural log of that concentration versus time. Yes. We get the natural log of x over x naught is equal to minus kt. So when we plug in, or when we think about how we would deal with the half-life, right? We've got the time over on this side. And so we can say, well, at time 1/2, I'm still gonna have minus k because it's a constant, but then my concentrations are known to me. I have half of the concentration left over divided by x naught. And now these guys are going to cancel, and I'm just going to have natural log of 1/2 is equal to minus k t 1/2, right? And I can solve for t 1/2. And I can also remember that the minus sign, if I stick it on the other side here, I can invert my natural log and make it natural log of 2 over 1, and then the sign is going to change. That's where we get the natural log of 2. Did that make sense? This is one of those trigonometric identities.
Yeah, I mean, I'll be honest, my natural log, and I'm really bad at those. I haven't done it in years, and it was just pre-calc 1, so that's on me. I need to go watch the Khan Academy.
It's okay. You can just take my word for it that this is an identity.
Okay.
That if I have, and this is also true if I have natural log of one thing over another thing, a over b, this is equal to minus natural log of b over a. So anytime you switch those order, then it's it just changes the sign. It's also true that this would be natural log of a minus natural log of b. I mostly do not expect you to remember all of these things. I might put them on equation sheets if I'm expecting you to remember them. But I like to remind people about them because it's just another example of, you know, that math that we learned at some point actually coming into play, which can be a good thing for us to remember.
Yeah, absolutely.
And again, repeating it 6 times, right? And so by the 5th or 6th time that it comes up in our class, then you'll be like, yep, I'm on that one, right? Wow. So that's what it's going to be like. And they come up. Mm-hmm. You know, ask McKenna and Emily. They've had several classes with me, and these trig identities come up all the time. So I'll keep on mentioning them so that way they get more familiar. Anyhow, so that's where this natural log of 2 comes from instead of the natural log of 1/2 or minus natural log of 1/2. They're just the same thing. Okay. So we took the negative sign over here, we inverted it, and that canceled out the negative sign, and we had natural log of 2. And so then this is where we get that natural log of 2 divided by k gives us t 1/2, right? Okay. Now, we can do exactly the same thing if we want to do it for any other amount, right? What did we do? We just said, okay, here's where we're going to start. Let's go all the way down over to here. I guess it doesn't like going over pages. So we said 90%. no problem. If I have 90%, then on top, I'm going to have 0.1 times the initial concentration divided by that initial concentration again is equal to minus K, and we'll call it T90 instead, right?
Right.
So the same exact thing that we just did, these guys cancel out over on the left-hand side, or I can move it over here, I guess. That's equal to natural log of 0.1, which is natural log of 1/10. So now I can do the same thing I just did. I'll invert it with a negative sign, natural log of 10, or natural log of 1/10, it's minus natural log of 10 equals minus K T90. And now when I solve for, let's see, T90, those negative signs just cancel out, and I have natural log of 10 over K. This is all first order kinetics still, right? Because we're working from that first order integrated rate law.
In this example, you would know what K was? That's correct?
Mm-hmm.
Okay, then you
Yep.
just take the natural log and divide it by K.
Yeah, we have to know what K is to be able to find the half-life.
Okay.
So the strategy that we're doing here is twofold, all right? We have our first order integrated rate law, or if we were working with some other integrated rate law, we would just use our integrated rate law. And then we are also using this relationship of relating my concentration at some later time to my concentration now at the start at T0. Okay? Those are the two pieces that we used. And we could use them with this first order integrated rate law. We could use it for any, you want to know when I've used up 15%? No problem. You want to know when I've used up 68%? No problem. It's going to be exactly the same. I'm going to set it up. I'm just going to have 68% here instead of 0.1, or I'm going to not have 68. I'm going to have 1 minus 0.68, so 0.32, is that right? Yeah, so 0.32 is what's left, because that's what I'm relating, is I'm always just paying attention to what's left, okay? So I can use, for the integrated rate law, I can use this process for regardless of what quantity I want to know. How much time when I've used up 99%? Okay, no problem. It's just going to be 0.01 times X naught instead of 0.1, right?
Right.
So my process is exactly the same. And that's why I wanted to show you the process, because that's more empowering than me just saying, this is the equation. So.
Yeah, I appreciate it, because I wrote down a bunch of equations, but sometimes it's hard to pick where to pull it out.
Right. And I would much rather have you pick a strategy and say, all right, here's my strategy. So that's why I like sharing my strategies with you.
Yes.
Our strategy is twofold. We have to have an integrated rate law, and we need to know what the relative amount of stuff is that we're talking about, which means we can use this with other integrated rate laws too. So you ready for that?
I'm ready.
All right. So if we want to do something with, and we don't have to follow it all the way through, I think you'll be able to see the pattern. If we want a second order integrated rate law, then our second order integrated rate law is 1 over x minus 1 over x naught equals kt. Okay?
Mm-hmm.
So this is this little guy up here only for second order. So that's the number one part of our strategy. The number two part of our strategy is the same as it was before.
Okay.
If I say half-life, okay, I'm just gonna put in T1/2. And this concentration would be half of X naught. And now I simplify it. It's not quite as easy to simplify it, but I can still do it. I just have fractions to deal with, which is kind of irritating. But I can still simplify it, okay? So it's not quite as easy to deal with it, but it's still doable. And so that's why I wanted to mention it. We will almost never see anybody, messing around with second order or something, kinetics. There is an equation somewhere, I forget where it is, but anyway, it's probably in our book that has the equation for half-life. Because in this case, you do actually have to know one of the concentrations in order to figure out the half-life. We have to know a starting concentration.
Okay.
So we can't just, eliminate that term entirely, but you can still see the strategy. Strategy still works. So.
Okay. Yeah, I think this is a lot to look at. I appreciate all the stuff you went over.
Yeah, no problem. Are you finding, I know you were a little worried earlier in the week at the pace of new material. Are you feeling that things are settling out a little bit?
I don't know. I got some stuff I feel okay about, but I don't know. I think maybe it's just me, but just the pace that the stuff is, like the videos, like I said, the half-life was like 2 minutes. So going through a 30-minute video is taking me a couple hours, and it just feels like I know I'm supposed to be learning, but it's just like new thing. So some of that's just my background, I guess, but
I don't think it's just that, because this is a very, the videos are very intensive, and partly that's because I don't want you guys to have to watch me like for, I don't know, however long we would. But normally if we were meeting face to face, we'd probably be together for 2.5 hours, or 3 hours per day, 3 days a week. And so it is a lot of content, and I'm delivering it in fairly condensed videos. And so it makes good sense that you're taking the time to really, absorb them and sit with the material, because that is necessary in order to get it. So if you are finding, I have no problem with going through some of the other foundational material and stuff with you in more detail if you feel like you need it. That is never a problem. So
yeah, I probably do. I don't want to sound like I'm complaining, but this is all I do all day, and I haven't had a chance to go back and look at what I screwed up from the first week.
Well,
I shaved my head today, so that was a good start.
So I'm going through the quizzes. So I think I've got 3 of them fully done, and then I went through and graded the stuff that was easy to grade on the Moodle, and then the rest of the ones that I had to look at what people's explanations were before I could figure out, how many points I wanted to assign. That's what I'm doing now. So
yeah, I've got it writing that one off. I got like a 2 on the Moodle. I know it's going to go up from there, but
yeah, don't worry.
I wrote out all my equations instead of using Excel, and so I didn't answer like the last 4 questions.
Yeah.
So.
Well, I'm sorry, and that should get better on this next one, because you will know that you can take extra time if you need it.
I appreciate that.
Yeah, no problem.
I don't want to take any more of your time. I appreciate you taking some time out this afternoon for me.
Oh yeah, no problem. I'm happy that I can do it, and I'm sorry it just took until Friday. I'm gonna, last weekend I fought with this next week's lab a lot, and so I won't have to do that this weekend. So, all right, hopefully I'll be able to front load some of more of those instructional videos over the weekend, so that way I won't feel so much like I'm doing the same thing you are, where I'm like 7 a.m. to 9 p.m. doing
exactly.
Yeah.
So. I also wanted to let you know, did you know there's a shellfish farm out near Ptolemy Park too?
I think so. I think it was the one, so it's probably Taylor Shellfish. And I think they have both of those facilities. And when I emailed them last month, They talked about the Shelton location as being the one that we could visit. So I don't know if they just don't have a visitor center there. But anyway, we'll find out what works for them, and regardless, we'll get some fun outside time. And even if we can't visit them, we'll go somewhere with salt water.
Absolutely. So. Yeah. Do you need my email address to send me the video?
I have it on, so St. Martin, or, your St. Martin's email, if that works fine, then I'll just send you that as the link.
Yeah, that'll work great.
Okay. It'll take a little while for my computer to convert it and upload it. So it might be another hour or so before that.
No problem. I'll start working on my graphs in the meantime.
Okay. Sounds good.
Well, thanks again very much.
You're very welcome.
Talk
to you later.
Have a good afternoon.
Yeah, you too.
Thank you.
Huh?